This ninth set of lecture videos is going to cover topics relating to fluids. The goals for this chapter are calculate the pressure at a given depth in a fluid, analyze pressure using the hydraulic principle, distinguish between gauge pressure and absolute pressure, calculate buoyancy using Archimedes' principle, and analyze fluid flow and Bernoulli's principle. The first topic we are going to look at is hydrostatic pressure. Previously, we defined pressure as the force applied per unit area. The same thing is true when we are talking about fluids. In this case, however, hydrostatic pressure is the pressure that a liquid at rest exerts on a submerged object. The pressure will increase as the fluid depth increases. The pressure in a liquid only depends on the depth and the weight density of the liquid, not on the surface area in contact. If we want to solve problems relating to hydrostatic pressure, we will use the equation that pressure P equals the height or depth h times the weight density of the liquid d sub w. The weight density of the liquid can be found in a table. Let's take a look at an example calculation. Find the pressure at the bottom of a water-filled tank that is 8.00 feet high. Notice in this problem how we aren't given the dimensions of the tank. We don't care what surface area it covers because that has no effect on the hydrostatic pressure. The only thing that matters is the weight density of the fluid and the depth of the fluid, which is what we are given. First, let's write down the data. We know the height of the fluid is 8.00 feet. We also know we have water, so we need to use a weight density table to find the weight density of water. Looking at the table, we see the weight density of water is 62.4 pounds per cubic foot. As a side note, the table you might look at will also have mass densities. We would need to turn the mass density into a weight density by multiplying by 9.80 meters per second squared. For our purposes, I won't give you problems where you need to use a mass density and turn it into a weight density. In this problem, we are trying to solve for pressure P. The basic equation we need to solve this problem is that pressure is equal to the height times the weight density of the fluid. Since this is already written in terms of pressure, this is also our working equation. Last, we can substitute and see that we have P equals 8.00 feet times 62.4 pounds per cubic foot. Multiplying, we see that we have a pressure of 499 pounds per square foot. We have units of pounds per square foot, which we don't typically use when talking about pressures. Typically, we use pounds per square inch or PSI. So we are going to convert pounds per square foot to pounds per square inch because we relate better to PSI. We can multiply by the conversion factor. 1 foot is equal to 12 inches, but then we need to square everything because we have square feet initially. This gives us a final answer of 3.47 pounds per square inch. This concludes the first part of our discussion on hydrostatic pressure.